This lesson is for Mrs. Cucci's College Now Pre-Calculus class. Today we're going to be talking about angles between vectors. So if you want to go ahead and get your notebooks out and ready, we'll get started. Okay, so what we're going to be talking about today is when a vector is multiplied by a scalar, the result of that is a vector. When two vectors are added, the result is also a vector. We might expect that the product of two vectors would also be a vector as well, but it's actually not. So we're going to talk about something called the dot product of two vectors. The dot product of two vectors actually is a scalar number or a real number. So this product is useful in finding an angle between two vectors and determining whether the two vectors are perpendicular. Okay, so let's look at what that dot product is. Okay, the dot product of two vectors, we'll call them U and V. Oops. Is U dot V. And what you do is you take the first component of each and multiply them, and then add the product of the second components. Okay, and when we do this, what we wind up with is a scalar value instead of a vector. All right, so let's look at an example of that. We're going to find the indicated dot product. We've got vector U, which is 2, negative 5, and vector V, which is 0, 4. And then lastly, vector W, negative 3, 1. First one we're going to find is U dot W. And then we're going to find W dot V. Okay. All right, so U dot W, again, what we're doing is we're taking the product of the first two components, so 2 times negative 3, and we're adding to that the product of the second components, 5, 1. So we get negative 6 plus a negative 5, which we know is equal to negative 11. Okay, so there's A. Pretty simple. It's not difficult. Okay, so now we have W dot V. So we've got our first component, negative 3 times 0 plus 1 times 4. And what we wind up is 0 plus 4, which is 4. So again, it's pretty simple. What we're also able to do with the dot product is the dot product can help us to find angles between two vectors. The angle between two vectors is what we'd say is the smallest positive angle formed by the two line segments or two vectors. So the angle, call it theta, between U and V is the same angle that's between V and U, which should make sense. It's just the angle in between the two vectors. Okay. Okay, so, sorry about that. So if theta is the angle between two non-zero, meaning they don't equal 0, vectors, we'll call them U and V, then cosine of theta is equal to U dot V over the magnitude of U times the magnitude of V. Okay, so let's take a look at an example. We want to find the angle between vector U and vector v. Okay, so what we're going to do first is we're going to find the dot product so that we can use that in our formula. So u dot v is equal to our first components, 3 times -4, plus our second component, the product of our second components. So we get -12 plus 14, which gives us 2. Then what we're going to do is we're going to find the magnitude of vector u. So it's the square root of the sum of the squares of each component, which is going to give us a square root of 58. And then we're going to find the magnitude of vector v, which again is the square root of the sum of the squares of each component. Okay. Once we have all that information, we can pretty simply use the formula we were given to find what we're looking for. So we'll say cosine of alpha, we'll use different variable, is equal to our dot product, which is 2, divided by the product of the magnitudes. Okay. We know to find the angle, we take the inverse. We'll put that right in your calculator and we get approximately 86.6 degrees. So all we have to really do is find what we need and then plug it in. Okay. Okay, so what we're going to do next is we're going to look at forces and equilibrium. Okay. All right, so when several forces act through the same point on an object, their vector sum must be 0 in order for a balance to occur. When a balance occurs, the object is either stationary or it's moving in a straight line without an acceleration. The fact that the vector sum must be equal to 0 for a balance and vice versa allows us to solve a lot of applied problems involving force. Okay, so let's look at an example of that. Suspended block is the example we're going to be looking at. Okay. A 350-pound block is suspended by 2 cables. And we'll draw a picture of this after. At point A, there are 3 forces acting. W, the block pulling down, and R and S, the 2 cables pulling upward. And outward. Find the tension in each cable. Okay, so let's draw a picture to describe that. So I've got, let's say this is a wall and this is a wall. Here's my box. You know, it's not a very good box. And I've got some strings that are attaching to the box, and here's my point A. Okay? So I've got a cable and a cable. This is my horizontal, as you can imagine. This box is 350 pounds. Okay. So we've got our force diagram drawn with the initial point of each vector and the origin. In order for there to be a balance, again, the vector sum has to be equal to 0. So what that might look like is we're saying my vectors that we're given are plus s plus w have to equal 0. So we can express each vector in terms of its magnitude and its direction. So we're going to go ahead and take a look at that. There was a little bit more information that's given to us here. I'm going to let you know that this angle here is 55 degrees and this angle here is 37. Which would make this angle here 88. Okay. All right, so what we're going to do is we're going to look at vector r to start. We want to find the magnitude of r. Okay. Now, again, r and s are the two cables pulling upward. Doesn't matter which one I decide to label r as. So why don't we'll make this one r. Okay. So what we're going to do is we're going to use cosine in order to find that. So we're going to say cosine of 125. Now where I'm getting 125 is this 37 plus 88, this angle here. Okay. And we're going to use I because that's my horizontal, plus sine of 125, J, which is my vertical. Okay. We're going to do the same for S. We find that magnitude. Cosine of 37, I, plus sine of 37, J, and then W, which again is the block actually pulling down. The magnitude of W is cosine of 270 degrees because it's pulling straight down. Okay. Think about where 270 is on that unit circle. Okay, straight down. I plus 350 sine 270 J. Okay. So that 125, again, we're going from here, right? From my horizontal, 125 is here, 37, and 270 is my force going down. All right, so what we wind up with when I kind of look at just this piece here, my magnitude of W, 350 cosine of 270 I, and cosine of 270 I, that's 0. Cosine of 270 is 0, so that piece is 0. And then because that force, right? .350 sine of 270. So I'm multiplying the magnitude of that force through. This whole thing becomes 0 because of this piece here. And I wind up with negative 350 sine at 270, which is negative 1. That's where I'm getting my negative from. So negative 350J. Okay. So substituting for RS and W and R plus S plus W equals 0, what we wind up with, and I know this is long, I apologize, guys. We're looking at the magnitude of R being cosine of 125 plus the magnitude of S, which is that cosine of 37. So really this should be R, this should be S. Here's my 37, here's my 125. Okay. There's my I plus magnitude of R, sine of 125, plus the magnitude of S, sine of 37, minus 350. J. And that's going to equal 0I plus 0J. Okay? And then actually what it does is it gives us two equations. So when we solve for R, okay, so substituting in this expression for R, the magnitude of R in that equation, what that actually looks like. Okay, so solving this equation for the magnitude of S, we actually get the magnitude of S to be approximately 201. Substituting in 201 for S, we get R, the magnitude of R, to be 280. And the tensions of the cables are going to be 201 and 280. Not overly concerned about this, guys. I know this was lengthy. We can go over it in class if that would be better. Okay. We'll see you guys tomorrow.